So my name is Fangjin. I am a co-founder of a company called Imply, and also I spent a lot of my career kind of working with open source technologies. So the topic of my talk today is about building an open source streaming analytics stack. So there's a couple of different open source technologies I'm going to talk about as part of my talk. And this talk is really going to focus on what these technologies are good for and how they can be put together for an end-to-end solution that's really good for a particular set of analytic use cases. So this talk, it will focus on the problem, the general sort of problem of working with large and complex volumes of streaming and batch data. And then the three sort of components I'm going to focus on. One is a component to do message delivery. The second component is going to be around data processing. And then the third component is going to be focusing on a system to serve queries. So to start out with the problem, if you guys work in enterprise, you've probably seen that today data sets are increasingly getting modeled as streams. And they're getting modeled as streams because a lot of data is just generally generated by machines or generated by systems or generated by users interacting with products. And today there's a lot of technology that basically allows this data to be modeled as a stream and to be delivered and processed and also queried in kind of its streaming form. So if you've ever worked with machine data or network flows or security data or click streams or even business metrics, you've probably seen this general trend happening. What you've also probably seen is these streams of data are getting more and more complex and also growing a lot in scale. And oftentimes when we talk about streams, you might think about real-time analysis and trying to analyze events soon after they occur. But in a lot of real-world use cases, what you see is both real-time analysis and historical analysis is important. So you may want to know what's happening right now and also be able to correlate that with things that are happening in the past. So when you look at the type of data that I'm really going to be talking about here, I'm really going to be talking about event-oriented data. These things are often called messages. Sometimes they're called logs as well. And this data generally has three components. One, there's a timestamp. Usually event-based data has some timestamp indicating when some event occurred. Usually in this data as well, there's a set of attributes. So these attributes are just various properties that describe the event. And sometimes these attributes are also called dimensions. And actually, very soon, I'll just show you sort of an example of what model data looks like. And the third component is something called measures or metrics. So these are attributes which are generally numeric. And they're numbers that may be of interest. So you might want to be adding these numbers up or crunching some sort of statistics around these numbers. So the typical workflow that we do with streaming data or this event-oriented data is we want to do some aggregations. We want to calculate a variety of statistics. Maybe we want to group and filter on the attributes and then make decisions on the findings of the data. So let me kind of show you an example here. I just have a UI which is using a public data set. In this UI, what I'm actually loading is edits as they're occurring on Wikipedia. And this is a public data set to kind of showcase what you can do with like a stream of event-oriented data. So with this data, there are a set of attributes or dimensions. With a Wikipedia edit, this might be the page that's being edited by somebody, the user that's doing the edit. It might be the geographical location of the user or any other thing of interest to us. And then for the measures, the numeric things that we care about, for Wikipedia edits, it might be the number of edits that have occurred, the number of characters that were added, the number of characters that were deleted, or maybe the number of unique users that we've seen over some period of time. And when I mention analytics, it's kind of this like kind of broad topic. The analytics I will be focusing on really for this talk is this idea of taking this event stream and being able to slice and dice it and drill into it and really be able to explore and understand what's happening. This demo is kind of built with the open source stack that I'll be covering in more detail for the rest of this talk. But to give you an idea of some of the operations that we want to do, maybe we want to understand like, over a period of time how many edits have occurred. So on Wikipedia, on the latest day, we see there's about 500,000 edits that have occurred. Maybe over the last 7 days, we see there's about 3.5 million edits have occurred. All this data is kind of getting streamed in real time right now. So maybe we want to look at like some just ad hoc, arbitrary, recent region in time. And we just selected some ad hoc region where about 2 million edits have occurred, and maybe we want to understand like what are the top pages that people are editing on Wikipedia. So we go into there and we see a lot of the top pages are basically internal Wikipedia pages. So as part of our analytics workflow, maybe we want to understand like let's filter out these internal Wikipedia things and look at just the articles on Wikipedia, because those are the main things that all of us look at anyways. And I guess very recently, Thor Ragnarok getting a lot of edits in there. Kevin Spacey, obviously he's been in the news. The Manhattan attack, I guess, has been pretty recent. Maybe we want to like drill into our data a little bit more and like try and understand, okay, well, what about just those English articles? So it looks like the English articles is about movies, music awards, and World Series, people dying, that sort of stuff. So if you're familiar with SQL, what we're kind of doing is like grouping on the data. Maybe we want to do like multi-dimensional analysis, and for each of the top users, we kind of want to understand, for each of the top pages, who are the top users kind of doing edits, and this is like a multi-dimensional group by. Maybe we want to like just filter on one particular user and look at like what other pages this user's also editing. So this particular user that I kind of drilled into is really into editing movies, popular movies. So this workflow of taking a stream of data, breaking that data apart, looking at it from many different angles, crunching a bunch of different metrics, this is sort of the workflow that we're going to be talking about and the various technologies that can make this workflow possible. So when it comes to making sense of a large stream of data, I generally break the problem down into 3 different areas. The first is around event delivery. So you might have all these servers that are generating a ton of events, and you have to get these events from where they are created to some place where they can be processed further or analyzed further. So event delivery is the first problem we're going to cover. The second problem is around event processing. A lot of data, when it's generated in its raw form, might not be that useful. There's a lot of enrichment that we want to do to it. Maybe there's more complex ETL that we're going to apply to the data. And when we're working with a large stream of data, there's a class of systems that are basically dedicated to event processing. And then the third main problem and the third sort of technology component I want to be talking about is just around querying this data. Like what kind of storage models and architectures make sense for handling large streams of data. And you might be wondering well, why are there 3 dedicated components? Why are there 3 technologies you're going to be talking about? For a small volume of data, you don't really need to put a bunch of technologies together and build a stack. However, when you have a very large stream of data, even a seemingly simple problem of getting an event from one place to another can be very difficult. There's a lot of problems that you can face around just what happens if the event is dropped, what happens if you lose your network connection, and various things like that. So even seemingly small problems at scale require dedicated systems. The stack, as it's going to play out, is basically we're going to have data that's being created. It's going to get streamed through a delivery system, processed through a processing system, and ultimately end up in some place where we can query that data and where applications and users can then make sense of the data. So data delivery, I think data delivery is one of the core pieces of building any sort of stream-oriented analytics stack. In data delivery, the purpose of a data delivery system is basically to get data from where it's produced to some place where it's going to be consumed. So on the left-hand side, we have a set of data producers, and on the right-hand side, we have a set of data consumers. Data delivery can be pretty challenging at scale. There's a couple of different problems to consider. One is, as I kind of previously mentioned, you might have a network outage, which causes a bunch of events to be dropped. And if your data is very critical, you want to make sure that you're always getting events and not losing any events. Another challenge that comes with data delivery is what happens when the thing that's supposed to be consuming the data fails. Like, if that thing just goes offline, should your data be dropped? Obviously not. You want to be able to maintain delivery of your data regardless of these consumers being up or not. Another challenge with data delivery is sometimes you might have multiple consumers. So you might have multiple systems that want to intake the same data set. You might have a system that's doing processing, another system is doing storage or whatever. So you have to consider, how do you deliver the data to not one system but many systems? And then obviously a common kind of problem throughout this entire talk is just around scale. If you have small volumes of data, a lot of these problems are a lot simpler, but at scale and working with distributed systems, the problems become magnified. So the data delivery system that I think is probably the best in class or best well known is Apache Kafka. If you guys don't know Apache Kafka, it's an open source project that was initially created by a team out of LinkedIn. There's a company nowadays called Confluent that is monetizing the work behind Apache Kafka. So how Apache Kafka works is it's a message queue or message bus. There are a logical set of things that produce the data, which are just kind of called producers. And then there's a set of things that consume the data called consumers. And one nice property about Kafka is it has an isolation between things that produce the data and then the things that consume it. So data is produced and stored on Kafka. Kafka is a distributed system, so it has basically partitions for storing messages. So producers will emit their messages. They'll be stored locally on Kafka in these partitions in a grouping of messages called a topic. And then consumers can subscribe to topics and be able to consume data from Kafka. So one nice thing about this is if your consumer goes down, it's not a big deal. The producers can keep producing messages, and they'll be stored kind of locally on Kafka. And Kafka retains these messages for a given period of time. And when the consumer comes back up or is recovered, it can reconsume messages based on an offset that is maintained within Kafka. So Kafka, what it's kind of famous for is it's very good for doing high throughput event delivery, so just getting a lot of events from one place to another. Most recent versions of Kafka, I think the most recent version, actually now promises exactly once event production. So the idea is getting an event, for a thing producing an event, it can now be delivered to Kafka basically in exactly once fashion, which just means that you're not getting duplicates or not getting messages dropped. Kafka has a pretty straightforward, reliable design. If you guys are interested, there's a lot of material online about how it works. And what's really nice about Kafka, it has this ability to basically buffer incoming data so that consumers can consume this data at different rates and at different times as well. So I think today Kafka is becoming a standard. There's equivalents in Amazon called Kinesis, and Google has PubSub, but the architecture of Kafka influenced a lot of the designs of these PubSub systems. And I think Kafka is a really great open source system if you're looking to do event delivery at scale. The next class of systems I want to talk about is a set of systems designed to process the data after it's delivered, and these are stream processing systems. So as I kind of briefly touched upon, raw data in its created form is often very difficult to use. It has many imperfections. It has nulls that might want to be replaced with an actual string value. It has a variety of things that need to be cleaned up. And processing systems, what they're most dedicated to doing is some transform on the data. So you basically want to apply additional business logic to your raw data, or clean up that data such that it's generally better for querying. Today, there's many sort of popular open source systems that are designed to do stream processing. Flink is one that I see is very popular nowadays within a number of different organizations. Spark Streaming is another stream processor. There's Apache Samza, and then there's Storm and Apex and many others as well. For this talk, I'll probably focus mostly on Samza because it's a stream processing system that I have a lot of experience with. So when it comes to stream processing systems, there's a set of challenges associated with them as well. One is scale and high availability. They're always going to be there when working with distributed systems and working with a high volume of data. Another sort of challenge related to stream processing systems is oftentimes the transform that you want to do on data isn't just one step. It might be multiple operations on a very large stream of data. And each operation may be very different from the previous operation. So each operation may have very different resource requirements. For example, one of your operations might be a join. That will have very different characteristics than an operation that's like replacing a null value with some default string. So good stream processors will usually consider the fact that the operations that are performed on the stream can be very, very different. Apache Samza is an open source stream processing system. It's actually also created out of LinkedIn. It's created by the original team that created Kafka, which is how I initially started working with it. And I think the architecture is one that makes a lot of sense to me. The idea behind Samza is you have an input stream of events, and then there's a set of tasks that you can apply to that stream. You can have one or more tasks, and each of these tasks is something that you program, whether that's a transform or a join or something of that nature. And each of the tasks can actually be fine-tuned with different resource requirements. So you can tune the task very differently, which makes it really nice for a lot of like real-world operations. And as the output of a task, you have another basically stream of data. So one way of using Samza is you have an input stream of data, you apply some operation to it, and then you have this output stream, which you write back to your message delivery system. And then from that output stream, it might become the input stream of another task. And you basically have this set of tasks, one after the other, which get applied to a stream of data. So yeah, the nice thing about having this task-oriented way of dealing with streams is it has very nice operational characteristics. As I mentioned, you can fine-tune each of the tasks. You can give the tasks different resource requirements. And then usually you can diagnose each task individually. So when you have a more complex data pipeline, you can diagnose and really fine-tune every stage of that data pipeline. Okay. So the next stage, so we kind of covered data delivery, which is getting events from one place to another. We covered processing, which is cleaning up that data. And the next component I want to talk about is really now getting this data into something where applications and users can query it. So querying this space is probably the largest and most complex because there's so many different systems that are basically targeted towards querying. And there's also a lot of different challenges that are associated with querying. I don't really have time to kind of go into a lot of different systems or a lot of the use cases you can do with querying. For this talk, I'm just kind of focused on the analytics component that I demoed earlier on. So when doing analytics on a high volume of data, obviously the challenge of availability and scale is always there. But beyond that, there are challenges around just sort of interactive analysis of the data. So when I say interactive analysis, what I really mean is if you put some sort of application or visual thing on top of your stream of data, generally you want to be able to interact with that data in a way where the actions that you do on the data are almost instantaneous. So we're going to try and target sub-second queries on the data. And even though we're talking about streams of data, both real-time and historical analysis is important. So sometimes we want to know what's happening right now. Sometimes we want to understand, is what's happening right now substantially different from what occurred in the past? Working with large streaming data sets, a common problem comes up when we have high dimensionality and high cardinality. So what high dimensionality means is what happens when we have not just like tens of columns, but hundreds or even thousands of different attributes that we have to consider. And the high cardinality problem comes up when we have millions of unique values per each of these dimensions or per each of these attributes. And if we're trying to group bys and sorts and order bys, when we have a lot of dimensions and we have very high cardinality for those dimensions, queries can be very slow. So there's various things we can do to try and speed up queries. And then the last problem that's kind of facing querying systems is this idea of ad hoc analysis. So when you have many, many, many dimensions, you don't want to pre-compute out all your queries. You want to be able to do ad hoc kind of slicing and dicing and aggregations on the data. So when you have an analytics system that basically solves these challenges, what it allows you to do is allows you to basically have a dialogue with your data. So you can ask your data a question, you can get an answer back, and maybe that answer helps informs further questions. So in that demo I kind of showed in the very beginning, kind of just exploring Wikipedia data. The idea is to be able to slice and dice and like look at your data from many different views and many different attributes to be able to understand what's happening. So the open source system that I work on and I want to talk about is a system called Druid. Druid is also under the Apache license. It's initially created to be able to intake streams of data from Kafka and Samza and other streaming systems and be able to do a lot of these like slice and dice queries and aggregations. So Druid stores data basically in a column format. And each column has kind of a type associated with it. That column might be a string, it might be a number. And depending on the type of column, there's various like compression and encoding algorithms that get applied. Druid is an open source system that's designed for these sub-second ad hoc queries. And how it gets its performance is in part based on how data is stored, and in part based on the fact that it can use both exact and approximate algorithms. So Druid today, it's probably used by over 1,000 companies in production. There's a lot of famous ones that have talked about their public usage, much like the other two open source systems I talked about before. I'm not going to go into like the full details of how Druid works. I'm just going to kind of talk about it at a high level because it's a little bit more complex than the message bus and also the stream processor. A very high level, Druid basically takes raw data and then it indexes it and creates these immutable time partition shards called segments. And what a segment is, it's basically a global index of a time interval to some mapping of data. What that means is very high level. Druid is very good when you have a timestamp and filtering on exactly the data that matches a time interval and matches the data that maps to a very specific set of queries. So within each segment, within each shard, the data is stored in a column orientation, and then each column is compressed depending on the type of data that is getting stored. And then each shard also contains a lot of indexes for fast filtering. This is not unlike a lot of other column-oriented data stores out there. However, what it is pretty good for is being able to handle a very large stream of data. Druid also supports a bunch of different types of approximation algorithms to make queries really fast. It supports hyperlog for distinct count. It supports top-end queries for basically doing rank and order type queries. It supports approximate histograms and quantiles and other sketch algorithms that are primarily designed to work with sets. The architecture of the system is probably what's more interesting. So the idea is that you have data that's in a stream, and sometimes it can be in a file as well. And that data gets streamed directly into a set of processes called indexers. The indexers take the stream, and then it creates this shard that Druid calls a segment, and these segments get loaded across a set of historicals. These historicals are basically responsible for answering queries on data, and that's all they do. At a very high level, we also have a set of brokers which do scatter-gather functionality. So there's three main processes kind of associated with Druid. There's the stream that comes in. The indexers build it and turn it into a format that's very good for queries. The historicals answer queries, and then the brokers kind of forward queries from various applications and clients. So kind of putting this all together, the stack that I alluded to at the very beginning, the data delivery piece, I think Apache Kafka is really great for doing data delivery. The processing piece, I think Samza is really great for doing processing. And then for the querying piece, Druid is handling the querying piece. And they're kind of logically lined up where you have raw data on one side, and then At the very end of it, you have applications and users interacting with the query system. So I thought it might be useful to basically go through an example, a real-world example of how you take a raw data set and then use these systems to do something useful with it. So the data set I'm going to be talking about is basically advertising data. This is, for most companies in Silicon Valley, they're working on something related to advertising. So the input data is going to be basically two sets. One is called an impression stream. This is people that might be viewing an ad. And the other set of data is a click stream, which is someone that might be clicking on an ad. And at the end of the day, what we want to understand is, for a stream of impressions, how many people actually clicked on an ad. So for the number of people that viewed an ad, how many people clicked it. And you might be thinking, well, I've worked with databases before. Why don't I just put both impressions and clicks in a database and do a join query? That seems like it would solve all the problems. Why go through the process of setting up this entire stack? And the idea is if you have a low volume of data, you can do that. However, if you're working with a live impression stream that might be 1 trillion events over the course of a month, and your click stream is several billion events, which it is for some of the largest technology companies out here, that join query that you're going to try and do is going to be very, very, very expensive on the query side. So instead, we're going to look at some strategies of being able to do the join at the stream processing level, such that our queries are going to be able to complete in still less than a second. So basically, we're going to take these two streams of data, one that's people looking at ads and one that's people clicking on ads. And what we're going to do is a variety of different things. The big thing is we're going to join these impressions with clicks. And another big thing is we're going to do some transforms of the data. So we might take IDs of advertisers and publishers and convert them to human-readable string values. We might take things like geocodes and convert them to actually country or state string values, and a lot of other cleanups of the data. So looking at our message bus, basically, we might have some ad servers, and one set of ad servers is going to be feeding this impression stream into Kafka, and another set of servers is going to be feeding clicks, basically, into Kafka. So in Kafka, we have two logical data sets or two logical topics. One's called impressions, and one's called clicks. And at the end of the day, we want to get a joined data set between impressions and clicks into our query engine where users can start interfacing with it. So within Kafka, usually what an impression stream is going to look like is there's some ID or key identifier of it, and then there's going to be a variety of different dimensions and timestamps and other attributes like that. And our click streams, we're going to have another ID, which is our join key. And this ID is basically mapping to some particular ad. So we're going to leverage our stream processor to try and do the join between the value, the event that's in the impression stream, and then the event that's in the click stream. And the first step, sort of the first task we're going to create in our stream processor is the shuffle step. And the idea of a shuffle is to relocate events such that they can be joined. So the idea is we're going to create a unified stream of data where all the click keys and all the impression keys that are going to be joined kind of end up in the same logical partition in Kafka. And this makes our join a lot easier for later steps. So the shuffle step is the first step we're going to do, and at the end of the shuffle step, we're going to have this new topic within Kafka that's called the shuffle topic. So it's another data source within Kafka. From this shuffle data stream in Kafka, we're going to send it once again to our stream processor, and we're going to have a secondary task that's going to do the actual join between the events. And the idea behind the join is we're going to basically remove one of the events, and we're going to add this new attribute, which is called isClicked. So if you look back here, these two events are going to be joined together, and we're just going to add, for one of these events, we're just going to add a new field that basically says isClicked is true. And obviously, if a corresponding If a corresponding click is not there, then we just set is clicked is false. So that should hopefully be pretty straightforward. At the end of the join step, we have now an additional topic kind of within Kafka. That's the join stream. And at the end of this, the join stream is once again going to be sent to our stream processor, where we now have a third task. And this third task is going to take the join stream and then perform all the enhancements and other business logic we want to apply to the data. And at the end of this output stream is going to be sent directly into our query engine. So yeah, the query engine obviously is then going to handle a lot of the analytics and aggregations, a lot of the slice and dice that I kind of demoed at the beginning of this talk. So I hope you do try this at home. I mean, obviously all the technologies I've talked about here are all open source. Here are the web pages basically for each of the open source technologies. If you want to check them out, each of them have their own sort of independent communities and maintainers of the projects. Cool, so kind of reaching the end of the talk here. Basically what I hope you got out of this talk is managing a large and complex volume of streaming data is very difficult and oftentimes requires dedicated components, each dedicated to solving a specific set of problems. I talked about using Kafka for basically delivering your events from one place to another. I talked about Samza for doing stream processing and kind of cleaning up the data. And I also talked about Druid for doing interactive exploration of the cleaned up data. Cool, thanks everyone, and happy to take some questions right now. Yes?
So in case of ad impressions, that time frame between impression and click is usually pretty short.
Right.
How do you deal with like ones where it could be a little bit longer period where you're getting, it could be like hours or days between that?
Yeah. So most of the joins that happen in the stream processor tend to be a window join, and what that just means is I didn't really get into all the technical details, but usually if you have an impression, you buffer it for a certain period of time, and then you wait for the click to come. And that like buffering time is basically, it's not going to be forever. It's going to be some defined window of time. And one of the challenges, if that click event comes like 2 days later, basically you're going to have slight inaccuracies in your data. And that's sort of the nature of doing these sort of stream processing jobs. The way to really get around this is you should periodically have some sort of job which is taking your raw data and like cleaning it up and maybe doing some sort of batch processing around it. This is what's known as more of a classic Lambda architecture, where beyond just the three components that you have, beyond just the three streaming components, you also have some static batch component in the background, which is taking your raw data in batch form and then cleaning it and creating the golden copy of it and reloading it into your query system. So short answer is, with stream systems, sometimes you have to live with a little bit of inaccuracy, especially for delayed events. Yes? Right, so the question was around comparing Druid to Redshift. So I'd say that probably the biggest difference is, one, Druid is very optimized for like streams of data. So if you want to just stream a data set directly in from a message bus or a stream processor, you can do that very low latency ingest. On the query side, the biggest difference is probably around the OLAP capabilities, the slice and dice and aggregation capabilities of the engine versus Redshift. So Redshift is much more of a classic data warehouse where you can do all queries and they might take however long they take, whereas Druid is a system that's highly optimized for sub-second queries. So if you're focused on like visualizing the data or powering some sort of application, or like very low latency use cases, that's what it's really designed to do. Yes? So the question, I think, was how does the query engine integrate with Flink and other stream processors? So for Druid specifically, it works with Flink out of the box. It's sort of the interface is pluggable. The best ingest characteristics are always with message buses, so we can do like exactly once ingestion from Kafka and Kinesis and other things. But you can also stream in data directly from Flink and Storm and other stream processors. It's sometimes the delivery guarantees are not always 100% the same. Any other questions? Yes. So in the architecture that I talked about, so Kafka has a configurable retention mechanism basically associated with it. I believe the default is 7 or 14 days, something like that. So it has some notion of buffering. If you, like, I wouldn't recommend basically using it as a file system, because if you want to retain data that's like years into the past, it's not really designed for that. The common mechanism is people might just be writing data from a message bus like Kafka directly to a file system like HDFS or S3 or something of that nature. So I can hear the... Right. So the question was around, what if I want to process 1 year of historical data and put it into a system like Druid? You probably wouldn't use the stream setup that I talked about. I mean, that's just really for a live stream of data. I didn't get into it in this talk, but a system like Druid does have a batch loading mechanism. So it can actually, you can actually leverage MapReduce to process a bunch of static files and load it into the system as well. So it is supported. It's not what you would do for like a set of streams. But yeah, batch loading is supported. Yes? Right. So Druid is a system. So the question was, how much work does it take to basically get a data set in that doesn't have a primary like time column? So Druid is a system that's like definitely very optimized for time and can do a lot of optimizations. Basically, if there's a primary time column, it can like smartly filter the data. If that like primary time column doesn't exist, that's also fine. Basically, Druid just make up one for you. It just creates like a default value and to get the data in, and then not be able to leverage some of the optimizations it has. But there's secondary indexes that are basically created for filtering on string values and for being able to slice and dice your data. It's just that first level pruning based on time would not occur. Cool. Any other questions? Oh, one more. Yep. So the question is, how would you set up the stack in something like Amazon Web Services? So each of the projects usually has like documentation related to it. All three projects I talked about are like JVM-based projects, so they can all be packaged as a tarball and really deployed in any like Linux environment. For Kafka and Druid, there's like actually dedicated like cloud Amazon-based deployments that are available already. And I'm sure if you dig through the Samza docs, they'll have docs about like how do you deploy this in AWS. So the short answer is the product documentation covers it, and it should cover it in a lot of detail because most of the time these projects are getting deployed in AWS. What is the URL for my example? You mean this UI that I showed? So this is at demo.imply.io. So this is just a quick example we whipped up on like a public Wikipedia data. But interestingly enough, the Wikimedia Foundation itself does actually use some of the same technology to analyze like how people are interacting and viewing Wikipedia pages and other wiki things. So yeah, you can check that out if you're interested.